Imagine waking up tomorrow and finding out that every star overhead, every byte of memory in your mind, and even your own body might be nothing more than computational shortcuts inside a massive simulation. At first it sounds like science fiction. But in 2024, quantum experiments with neutral atom simulators and advanced superconducting processors are tackling many body systems at scales once thought impossible. And Donald Hoffman's cognitive models suggest our perception itself may hide the real truth. Between surprising physical evidence and radical thinkers, the possibility of a designed reality isn't just imagination. It raises uncomfortable questions about why the universe looks so precise. The strange case for a designed reality. When researchers turn from speculation to evidence, they encounter what might be called the strange case for a designed reality. If the universe truly emerged without guidance, why do so many of its properties present as ordered, structured, and finely balanced? For generations, scientists and philosophers have puzzled over why the laws of physics remain so consistent, and why the large-scale patterns of the cosmos display symmetries that appear to exceed what chance alone would suggest. Instead of encountering chaos at every scale, we face a reality marked by coherence, raising questions about whether this coherence serves a deeper purpose. To investigate this, we need to clarify what design means in this context. It doesn't have to imply a conscious creator in the traditional sense. It could mean an architectural logic behind the fabric of reality, a computational framework that produces matter, energy, and space as configured outputs. In cosmology, researchers expect broad statistical homogeneity once you look at the universe across sufficiently vast scales, yet some observations challenge this expectation. Surveys have reported structures and alignments larger or more coherent than the standard model anticipates, provoking active debate. Likewise, studies of the cosmic microwave background, the faint afterglow of the Big Bang, have uncovered curious alignments and anomalies. While these do not overthrow cosmology, they remain persistent enough that scientists continue to probe their meaning. This persistence is critical. Randomized processes should trend toward disorder. From stellar evolution to radioactive decay, randomness plays a key role in shaping how systems evolve. Yet the data sometimes suggests that order not only resists decay but reasserts itself. Anomalies in the microwave background, for instance, exhibit patterns that do not vanish after correcting for known sources of interference, such as galactic dust or infrared contamination. Researchers find that certain low multipole alignments, the so-called axis of evil, survive across data sets, appearing with statistical significance beyond what random chance would typically yield. Whether these anomalies represent physics we don't yet understand or hints of something deeper is contested, but their stability continues to draw attention. It is here that the suspicion of intentional structure arises. If the universe is nothing more than random processes expanding unchecked, why do these large-scale alignments recur? And while no single anomaly proves that reality is designed, the collection of such features makes the hypothesis difficult to dismiss outright. The idea of code-like underpinnings offers one possible explanation. In a coded system, exceptions to randomness may appear not as errors but as programmed conditions, rules designed to ensure stability within the simulation. Still, caution is required. Some published analyses report very low p-values for specific cosmic microwave background anomalies and fine-tuning puzzles, but their interpretation remains debated within the scientific community. Low probabilities alone do not prove design. They do, however, reinforce the fact that our best models face significant tensions. Cosmological data continues to challenge assumptions, and many researchers frame these puzzles not as evidence of a cosmic architect, but as opportunities to refine our theories. The fine-tuning of physical constants highlights the conundrum from a different angle. Consider gravity. If the gravitational constant were only slightly weaker, stars might never ignite. If even a bit stronger, stars would collapse too readily into black holes. The electromagnetic interaction determines the chemistry of atoms. Adjusted only a fraction in stable molecules, and by extension life would never form. Researchers studying fine-tuning emphasize this razor-thin range of viable values. These constants appear extremely sensitive. Small deviations obliterate complexity. That sheer fragility brings us back to the original puzzle. Why do the constants exist in precisely the values that allow complexity and consciousness to emerge at all? One proposed explanation is the anthropic principle, which states that we see the universe this way simply because we exist within it. If conditions were otherwise, no observers would be here to notice. While logically valid, this does not address why conditions are available in the first place or why the physical laws operate with such precision. By contrast, a simulation framework reshapes the problem. In that view, tightly tuned constants are not improbable outliers. They are parameters established at the outset, just as values must be locked into code to ensure a functioning program. A poorly tuned simulation breaks. A stable one requires exact specifications. Skeptics argue that human perception tends to overemphasize order, seeing alignments and structure even where randomness suffices. Pattern seeking is a powerful psychological bias. However, there is a distinction between misperceived shapes in clouds and statistical alignments observed across billions of light years. The first is subjective, the second is empirical and intersubjectively verifiable. As new data arrives from higher resolution instruments, the tensions have sometimes sharpened rather than faded, leaving scientists to wrestle with whether more complex explanations are required. That tension also plays out philosophically. In science, the preferred explanation often requires the fewest assumptions. If known physics can account for the universe, additional claims of design appear unnecessary. But if the very framework of natural law depends on constants so specifically arranged that their spontaneous emergence strains plausibility, then invoking a single generative system like a simulation protocol may in fact be the simpler path. A single program that establishes order is arguably less extravagant than infinite improbabilities coinciding by chance. From this perspective, the case for intentional architecture doesn't rest on faith but on inference from data that resists easy dismissal. Reality may not reveal itself as wholly random. Instead, alignment, coherence, and sensitivity to underlying rules may hint at something more structured, something that, like code, governs behavior from beneath the surface. If the evidence points toward hidden instructions, then perhaps the boundaries of physics point beyond themselves. This brings us to a deeper question, one not just about how reality operates, but about how we perceive it. After all, even if the universe does contain coded rules, our access to them is mediated through our senses and our cognition. And here another challenge arises. What if perception itself does not give us direct access to truth at all, but only to a simplified model of it? Donald Hoffman's rule-breaking idea of reality. Donald Hoffman is one of the most provocative thinkers advancing a rule-breaking idea. The reality we perceive may not be reality at all. His claim sounds unsettling because it challenges one of our most basic assumptions, that our senses provide a direct link to the external world. Hoffman argues instead that evolution has never selected us to see truth. Our vision, hearing, and touch are less like windows onto reality and more like filters designed to highlight what helps us survive and ignore everything else. This framework is known as the interface theory of perception, and it radically reframes how we think about consciousness and the world itself. Hoffman illustrates the point with a simple but powerful analogy. Our senses act as an evolutionary user interface, not a window. Just as the desktop icons on a computer are not literal files but convenient representations of hidden code, so too the tree, rock, or apple we see is not the thing itself but a perceptual shortcut. The brain organizes experience into icons that mask underlying complexity. The appearance of solidity, color, or sound is a simplified symbolic system the mind has built to help us act quickly and efficiently within an environment. This shift in perspective becomes even more forceful when paired with mathematics. Hoffman and his collaborators use evolutionary game theory to model hypothetical creatures operating in simulated environments. Some are coded to perceive the world truthfully, while others are designed to perceive selectively, focusing only on cues relevant for survival, like signals for food, mates, or danger. Across repeated simulations, the selectively perceiving creatures consistently outperform those attempting to track the full truth. Hoffman formalized this result in what he calls the fitness beats truth theorem. Under the assumptions of natural selection, fitness, not accuracy, drives survival. From this, he concludes that organisms shaped only by evolutionary pressures will not generally evolve to see reality as it actually is. It's important to add a qualification here. Hoffman's conclusions follow from formal models, and like any model, they depend on specific assumptions. Critics argue that while the intuition is compelling, the generality of the claim is not proven. Yet the core point remains provocative. The efficiency of perception often comes at the expense of accuracy. By extension, illusions may not be faults in the system, but essential features of how our survival interface operates. Viewed this way, everyday perception starts to look suspicious. Take color, for example. Humans perceive a small fragment of the electromagnetic spectrum translated into experiences like red or blue. Physically, there is nothing red about a 700 nanometer wavelength. It is merely an abstract measurement. The redness you see is a coded signal, useful for distinguishing ripe fruit from spoiled or for adapting to the daily cycle of light. Likewise, objects feel solid to us, but physics suggests that what we call solidity arises from electromagnetic repulsion at the atomic level, not impenetrable matter. The solidity is a perceptual icon, reliable for action but not a literal description of the underlying structure. Hoffman extends this argument further, targeting even space and time themselves. The fabric of three-dimensional space stretched across time is, he suggests, another component of the user interface. Just as a computer screen presents a bounded, ordered layout that makes hidden files manageable, so our minds may impose spatial and temporal dimensions on experience. They help us catalog events, predict sequences, and store memories. In this framework, the apparent stage of reality, space-time itself, may be part of the interface, not the truth behind it. This leads Hoffman toward a bolder model, the conscious agent theory. If perception doesn't reveal physical reality as it is, then what sits beneath? Hoffman proposes that the fundamental substrate of the universe may not be matter or energy, but networks of interacting conscious agents. These agents are not biological creatures. They are mathematical abstractions representing entities capable of experience and choice, however minimal. The physical world we see under this theory emerges not as a base layer, but as a projection of interactions among conscious units. Space, time, and even matter may be emergent phenomena, the way icons on a screen are emergent from code. Not everyone accepts this leap. Some critics charge that conscious agent theory is speculative and difficult to test. Others argue that while the interface theory usefully captures how perception is shaped by survival, positing consciousness as fundamental moves the debate away from empirical ground. Hoffman counters that all scientific models rely on assumptions and that placing consciousness at the core is no more radical than assuming space-time or matter is given. Still, his framework remains controversial, yet compelling enough that researchers continue to debate its implications. Returning to the evolutionary side, the consequences are stark. Hoffman and colleagues argue that under the models applied in the fitness beats truth theorem, the probability of perceptions being strictly veridical is not just low but essentially non-existent within those formal systems. To phrase this carefully, the claim is not that reality can never be known, but that evolution does not, under those modeled conditions, optimize for accuracy. Organisms that attempt to represent the world in detail fall behind. Those relying on simplified cues win out. In survival, truth comes second to utility. That inversion upends the optimism many people project onto science, that we have been naturally granted the tools to see reality. In Hoffman's view, science itself may be a layered extension of the interface. Instruments enhance perception, but they still feed into brains shaped for survival. Data gets filtered, modeled, and translated into mathematical icons. Science may approach deeper structures, but it must remain aware that its foundations still rest on perceptual systems honed not for truth but for function. At best, it sharpens the resolution of the interface. At worst, it multiplies illusions and mistakes them for reality. And if perception is function-driven rather than truth-driven, then certainty itself becomes risky. The world presented to us, the colors, objects, distances, and timelines, might be closer to a constructed display than a mirror of existence. The striking point here is not that the world doesn't exist, but that the version available to our senses is deliberately simplified, and any confidence that it reflects deeper reality exactly is misplaced. What lies beneath could be stranger than we have words for. That claim doesn't end the conversation, it reframes it. Hoffman's models offer a theoretical backbone suggesting that stripped-down perception is the biological norm, and his conscious agent theory speculates about what fills the gap beneath the interface. Whether or not these models become accepted foundations, they highlight the need for caution when equating appearance with reality. Reality may not just be larger, but qualitatively different from what our senses describe. Ideas like this echo back against the earlier puzzles raised in cosmology. Order without obvious cause, laws too precise to be accidental, constants balanced on a razor's edge. If our perceptual world is an interface, then the anomalies in cosmic data may not be outliers within truth, but clues that truth itself hides beneath an interface we are ill-equipped to penetrate. This possibility opens a bridge between cognitive theory and physics, the suspicion that both point toward hidden foundations we cannot touch directly. Such possibilities set the stage for asking a different kind of question. If our biology prevents us from seeing underlying reality, could our technology give us a new path? The moment humans begin crafting machines that simulate the rules of nature on an unprecedented scale, the issue of what counts as real gains new urgency. And that is exactly where the conversation now leads. Quantum computers and the rise of synthetic worlds. What becomes striking in this moment is the emergence of machines that no longer just calculate. They begin to reconstruct the building blocks of the physical world. Quantum computers and simulators now allow researchers to recreate many-body quantum systems at scales that conventional machines cannot practically reproduce. These are not small demonstrations of abstract math anymore. They are working experiments where matter-like behaviors emerge from code and engineered qubits. To understand why this matters, it helps to recall the ceiling that classical computers hit. A classical processor manipulates bits, zeros, and ones arranged in linear sequences. Each additional particle or quantum element you attempt to simulate multiplies the complexity until even the most powerful supercomputers drown in calculations. Trying to model the interactions of a few dozen particles quickly becomes effectively impossible without shortcuts. Quantum devices, however, replace bits with qubits. Qubits exploit superposition and entanglement, allowing them to encode and process overlapping states simultaneously. The effect is not linear growth, but combinatorial expansion. This property means adding qubits does not merely extend capacity step by step, it multiplies potential pathways at staggering rates. It is one thing to say so in principle. It is another to see it in practice. In 2024, neutral atom programmable simulators were used to control systems of up to 256 individual atoms. These setups allow scientists to probe quantum magnetism and phase transitions in ways previously inaccessible. At the same time, superconducting and photonic platforms have reached into the range of tens to low hundreds of qubits for studying many-body dynamics. For instance, IBM hardware has run experiments with a 127-qubit device used in fields such as cosmology-inspired simulations, while collaborations have demonstrated quantum chaos in arrays of more than 90 qubits. Each example remains limited in scale, yet each also surpasses boundaries classical machines cannot cross in reasonable time. Together, they constitute a clear signal. Direct simulation of quantum processes at non-trivial sizes is now occurring inside engineered systems. This raises a profound implication. If we can already reproduce physics at the particle level within small yet coherent synthetic environments, then in principle more advanced architectures could extend these experiments outward, creating environments complex enough to be world-like. A synthetic quantum environment is not simply a caricature. It has rules, probabilistic outcomes, and measurable states that unfold under consistent laws. At small scales, this mirrors nature. At greater scales, it begins to resemble a constructed reality. The obvious question surfaces: if today's machines can bend toward creating tiny but authentic pieces of a universe, could tomorrow's create entire ones? There are practical boundaries, and it is important not to ignore them. Current hardware is notoriously fragile. Qubits decohere quickly, computations degrade under noise, and error correction demands far more resources than are yet available. Fault tolerance has not been achieved at useful scales. Reports from the U.S. Department of Energy and other agencies map progress toward logical qubits over the coming decades. Researchers recognize that breakthroughs are needed in stabilizing qubits, scaling up architectures, and reducing costs. That said, the trajectory is unmistakable. Experiments that seemed impossible 5 or 10 years ago are now routine, and the frontier expands year by year. The implications ripple outward. With even current capacities, quantum processors are opening doors in chemistry, enabling models of molecular interactions that could predict new drugs or materials more efficiently than laboratory trial and error. They can explore conditions relevant for superconductivity, energy storage, and biological processes. Every one of these applications points to practical synthetic arenas, laboratories built from calculation rather than molecules. Pulling back, when viewed through the broader context, these same tools hint at the possibility of engineered environments where every detail is internally consistent, governed by programmed laws. At that threshold, simulation stops being metaphor and becomes construction. It is natural that people react with humor when complexity breaches imagination. Some scientists liken explaining many-body simulations to describing the social entanglements of an enormous party. Every connection influences another, and even a small expansion overwhelms intuition. Heavy comparisons or jokes give a sense of scale where numbers otherwise fail. Behind the humor, however, is the extraordinary fact that humanity is now building devices capable of generating coherence among hundreds of quantum actors at once. That reality cannot be brushed aside as purely speculative. It is being demonstrated in laboratories with real atoms and real processors. The philosophical significance deepens here. Simulation theory once functioned mostly as a thought experiment, a way to stretch the boundaries of metaphysics in science fiction. But with machines that can already fabricate small physical-like domains, the discussion turns pragmatic. Humanity now holds a primitive version of the very tools that a hypothetical universe architect would wield. If the act of building systems that imitate physical law is feasible at our stage, then what becomes conceivable for civilizations thousands or millions of years ahead of us? The acceleration of the field sharpens the point. Unlike the gradual advance of early computing across mid-20th century decades, quantum technology operates with government backing, aggressive funding races, and global competition. Strategic narratives label supremacy in quantum hardware as a matter of national security. This pressure accelerates timelines. While consumer devices remain far off, laboratory capacities expand rapidly. Each new milestone means wider accessibility to synthetic environments, first for scientific insight, later potentially for educational or entertainment purposes. What feels exotic now may fast become routine, and with it the weight of the question intensifies. Are we uncovering the proof that an artificial universe is not only thinkable but achievable? In a sense, the irony writes itself. By pursuing computational control over quantum matter, we reflect the process that could have produced our own reality. Encoded rules drive particles, emergent laws govern behavior, observers arise within the system. When we engineer such conditions on a small scale, we mimic, deliberately or not, the principles that might govern the universe at large. At these scales, the ambition remains modest, but the conceptual bridge has been crossed. Whatever limits remain, the path from a handful of atoms to entire environments no longer feels impossible to conceive. At present, the modesty of scope matters. A system of 256 simulated atoms is infinitesimal compared to the astronomical number in even a grain of sand. Yet this comparison mirrors the history of computing. Early machines could barely factor small numbers in useful time, and now billions of transistors rest in every phone. Growth in these fields does not proceed slowly once key techniques are established. The nature of exponential scaling ensures that each increase in qubits or atoms accelerates the jump to larger domains. The distance from hundreds to millions or billions appears insurmountable when framed in today's terms, but history cautions against assuming progress stalls at early thresholds. So the real takeaway is neither hype nor dismissal, but recognition. Constructing worlds from code is no longer unimaginable. Fragments of this process exist now. Researchers stabilize atoms in arrays, entangle photons to model dynamics, and run computations that classical hardware cannot emulate. Each project erodes the line between describing physics and generating environments governed by physics. The conceptual leap narrows, from analyzing reality to manufacturing something that, within its scale, behaves with comparable internal validity. This recognition lends new gravity to what was once a playful philosophical hypothesis. There remains an even thornier implication. Once machines can sustain coherent synthetic worlds, how could one distinguish between a simulation and a natural environment from inside it? If emergent objects obey structured rules, if events unfold under consistent probabilities, then experience inside the construct would mirror experience outside. The more convincing the environment, the harder separation becomes. At some point, the observer has no means to declare one real and the other artificial. That boundary dissolves, leaving open the unsettling possibility that what we call physics could itself be the output of some broader architecture. And with this realization comes another, quieter question. If our own universe were structured like a program, would its architecture ever leave signatures, subtle hints in the data that point to its engineered origin? Cosmic glitches or programming shortcuts. If certain patterns in the cosmos appear less like noise and more like irregularities, the question arises, are these just quirks in our measurements, or could they signal limits in the deeper fabric of reality? In physics, they are usually labeled anomalies, departures from what theory predicts, but for those drawn to the simulation idea, they can look like shortcuts or optimizations, the kind of imperfections you might expect if reality were generated rather than absolute.